All right, looks like we have a quorum. Thanks everybody for joining today. My name's Tyson Witten. I'm responsible for product and solutions marketing within our API business unit, CA Technologies. Again, thanks for everybody joining today's webcast. As a point of housekeeping items, I want to make sure everybody understands that there's some Q&A at the end of the webcast. We're also going to be sending out the presentation tomorrow through email, as well as some relevant collateral. Today I'm going to be joined by Jamie Ryan, the Senior Director of Strategy for our API Management Business Unit at CA. Thanks, Jamie, for presenting with us today and joining the call. Excellent. So today's webinar, takeaways from API security breaches, I think is very timely. I think it's probably been very timely for the past few years. I think folks on the call and on the webinar most likely can see this within their own companies. Resources are really being organized around digital initiatives, if you will. It's this whole goal of trying to improve experience with your customers, right? Create this connection with them, some stickiness, right? Offering optimum value through digital initiatives, and what that means and how that's coming through is really mobile apps, mobile app development. You've heard the term omni-channel engagement, even the advantages of the Internet of Things. And so really these initiatives, what they're doing is that they're opening up access. They're opening up access to information, to data, but in turn, there's also this level of risk that's being incurred that organizations have to be aware of. And we can see this just in terms of evidence in our everyday lives and the daily news feeds that we're seeing. Companies are being directly impacted by breaches, API breaches, due to these initiatives. So today what we're going to do is we're going to discuss some of those breaches. We're going to discuss how risk mitigation steps can be taken to protect your APIs and your business. Jamie specifically is going to walk through not only proper steps to be taken to secure businesses and APIs by applying some mitigation steps in security, but in a way that doesn't inhibit business processes and allows for successful digital initiatives and API programs. And then Jamie's going to cover what to look for in an API management solution. So to get started, let's get this slide moving here. As I stated, these digital initiatives that are being taken on, it's what can be in the form of mobile development projects, omni-channel access across channels. It can be connectivity to devices or things, or even partner ecosystem connectivity. Each requires some connectivity point to access information with the enterprise, and that connectivity point is the API, the application programming interface. And the API has advantages, it has value on integration, development, user experience benefits, but it also poses some challenge, and risk being one. And so as the business opens up, as the API itself becomes really this attack vector of choice. And that's why for any API program, security is extremely important, and there's plenty of evidence to go around. Here's a list of some prominent API breaches you may have heard of over the past few years: Snapchat, Yahoo, Moonpig. These are examples of some breaches that hit the web, some of the .com space, some of the social media space as well. I think Snapchat's a great example. If you've seen that, social media company that develops private API, essentially has been developing private APIs to enable users to send videos or pictures or stories through its mobile app. The problem is that the private APIs can easily be reverse engineered. And so the background behind this scenario was this white hat organization, Gibson Security, this research group. They found some vulnerabilities. They attempted to alert Snapchat. It essentially went unheard, and eventually they posted that exploit detailing how to access users' personal information. Then another site called Snapchat DB used similar information to store those usernames and passwords. I believe for around, it says it right there, 4.6 million accounts. And Jamie's going to go through this a little bit more, but I think it's a great example just because you have a private API, it doesn't mean it's secure. You need the appropriate level of controls and security. Yahoo's another one. This is an example of an API breach, essentially where malicious actors, they gained access through an API, and then what they tried to do is attempt to identify what's called a bash vulnerability on 3 of their live sports streaming servers. Luckily, they weren't vulnerable. But again, I think this just points to the fact that security is needed at the API level. And there's more of these, all over the place. You can see Moonpig, if you're familiar with Moonpig. It's well known for selling personalized greeting cards in the UK. This is another example of a security researcher that alerted the company to a flaw in its API, which allowed hackers to see payment information and view addresses. In particular, this situation, every API request that was made, there was no authentication at all. So essentially, it allowed the ability to pass on any customer ID to impersonate that individual. And so you can see the risk there. Any attacker could easily place orders for customer accounts. They could retrieve card information. They could view saved addresses, view orders. And so, I think the interesting thing around this as well is that with a lot of these examples is that these faults and these vulnerabilities, they go unfixed for a number of months. And with Moonpig, I think it was about 17 months or so. But, it's not limited to the web or .com and social space. You can see on the right-hand side there, it also hits a lot of the other industries, energy, auto businesses as well. They're just as susceptible. Marva Power, this is another example of having the ability to change user ID values. So what could happen here was, attacker could easily reset any user's password and gain complete control of their account. And this is all done over the API. Tesla, another interesting example here. In this situation, the REST API was vulnerable. So that REST API essentially is enabling connectivity to what we like to call companion apps within the auto industry. So these are the apps that allow remote access to the vehicle to start the engine, unlock the doors, lock the doors, receive diagnostic information, and that API, that RESTful API, could be compromised and attacked through a brute force attack. So you can see some dire consequences in this situation. I mean, we're really not talking about just stealing personal information anymore, but serious safety concerns with a malicious actor gaining control of the vehicle. But there's hope, so put it that way. And not all API programs have to be dire. I mean, there are steps to be taken to mitigate risk, and that's why I'm going to hand it over to Jamie, and Jamie's going to talk through some practical security steps that you can take to prevent some of these breaches.
Thank you, Tyson. So now we're going to get a little technical and talk about some of the top vulnerabilities out there for APIs, and then we'll discuss the mitigation steps that you can take to make your API less susceptible to these potential threats. So what happens when an API is hacked? Often, to be honest, nothing really happens because no one knows that it's happened. So how do you find out that you've even been hacked? These vulnerabilities tend to surface only for a few limited reasons. One is maybe the publisher discovers it because of a well-known threat, a well-known vulnerability like Heartbleed or Shell Shock. So they go back and look at how their API was implemented, the tools that were used, and they see if they're vulnerable to that particular problem, well-known problem. Maybe by a white hat hacker. A few of the breaches that Tyson mentioned were first noticed by security companies and white hat hackers that actually tried to do the right thing and notify the company. And sometimes that goes unheard or unacted upon. But that's not necessarily going to divulge it to the public. But maybe the company's already been hacked and there's been a breach. You still rarely hear about these unless it becomes a PR nightmare. Though certainly in the last few months, you've probably heard about several of these, more than your fair share. And Tyson provided just a few examples. And let's put this in perspective. Public APIs are certainly the most well-known, but for every public API, there are many, many, many private APIs. Some people call them dark APIs, partner APIs, for every public API. And those are vulnerable too. And because they're private, the security might not get scrutinized as much. There might not be white hat hackers helping you out. People think, oh, these are just my APIs. I'm only providing them to a limited audience, to just my partners or to just my internal developers even. No one public is actually using them. But of course, if you've got an app out there, then everybody using the app is actually using the APIs. So we're going to talk about some of the top vulnerabilities, mitigations of API threats. Some of these are common best security practices for any application that can be accessed remotely, including web apps, dealing with psychological attacks like phishing, etc. But while they may look like obvious ones that apply across the board, we'll look at these 5 from an API-specific perspective and really dig in. So we're going to look at client impersonation, phishing, brute force, injections of all kinds, and unauthorized access or compromised secrets. And I'll relate them back to some of those publicized breaches that Tyson mentioned when they're applicable. So the first one is client impersonation. This probably has the most well-publicized breaches, and so it comes up again and again. What we mean by this, what we mean by client impersonation, is that an attacker reverse engineers a secret that's been assigned to an app. So the app is calling an API to retrieve some data, to register something, whatever the case may be. And what allows the app to be recognized by the API is some secret, usually a token or an API key. And if that app can be reverse engineered, that is, if you can sit in the middle and look at the calls it's making back to the organization, or if you can decompile the app itself and look at the code and extract that secret, it can then be used to make calls while pretending to be the original app. So you're actually impersonating a valid client. And once you're impersonating that original app, you can potentially do malicious things with that API. So we saw this with the Twitter keys that were used by third-party applications. And while this was blamed on OAuth, because it happened to be OAuth tokens that were stolen, that was a bit unfair. Realistically, it was simply an application that didn't adequately protect its secret. We also saw this with Snapchat, which many of you probably heard of, back when their estimated value was only about $3 billion. It doesn't seem to have hurt them much in the long run. I think the last estimate was $10 billion. But it was definitely a black eye at the time, and it was kind of a PR nightmare. And so we'll talk more about them in a second. And actually, this is pretty timely. Just this morning, I read about a hack of the Tinder API, if you're familiar with Tinder, that uses a bot to pair up heterosexual men so that they each think they're talking to a woman. I don't want to get too risque, but as you might imagine, it resulted in some really strange and overly aggressive conversations, which was the point for the guy who did it, but it was caused by a notoriously easy-to-hack API that uses only an authenticated Facebook credential for access control. So once you have that token, you can basically just pair people up and set up conversations as you'd like, and it resulted in some strange conversations. So what can you do about client impersonation? Well, the first idea, which seems a bit counterintuitive, is that you shouldn't try to make a public app confidential in the first place. That is, your app is either confidential or it isn't. If you publish your app on a public app store, like the iTunes App Store, it's public and people can download it and take their time to decompile it, to somehow otherwise figure out how it works. You can try to be clever, you can obfuscate the code a bit, but if you ship the app with a secret in it, you should be expecting that secret will become known. So from the API provider's perspective, there's very little value in recognizing that secret and making access control decisions around it, because the odds are it's not really a secret any longer. So you need to learn to let go of your app once it's published and use security mechanisms that don't require the client to hand over a secret token that's hard-coded into the app. Assume it's a public client. So if you're writing JavaScript for a web client, the browser has to be able to get the script file, use it in its HTTP calls in its user agent, which means that anyone can get that same file and see how it works and see if there's something in there that could be useful to hack your API. If your app is in the iTunes App Store or in Google Play, same deal. With apps, there are proxies that can actually sit between the app and the API endpoint and capture data flowing over the wire, often, in some cases, even if that data is encrypted. So you can actually spoof the certificate as well and capture that data as it flows over the wire. So that's what was used in one of the examples earlier with Kayak in order to reverse engineer the app's behavior. So it's definitely something to watch out for. It's a very common practice that people use these proxies to reverse engineer how the app interacts with the backend. And then most importantly, don't grant access to a resource based solely on the app's identity. So you need to require user authentication or other factors as well. So one last note here before I move on. Let me state this very clearly because it's a personal pet peeve of mine. An API key is not a security mechanism, even though many API publishers, app developers, even other API management vendors treat it like it is. So let me repeat that again. An API key is not a security mechanism. At most, it should be used as a counter or a way to loosely tie an application from a particular third-party development organization to certain rate limits, SLAs, monetization options. And even then, it needs to be combined with other mechanisms like hash-based validation to even provide that much identification. So to even trust it that much, you need other things involved. So security should go far beyond just an API key. It should include transport layer security, user-based access control, threat protection, and a really strong awareness of the user, the app, the device, and the relationship between those three parties. So I mentioned that you can't make a public app confidential. So this is mitigation number 2 for client impersonation. That doesn't mean you can't make a confidential client. So by definition, this would be an app that has the ability to obtain a secret confidentially. It's not hard-coded into the app itself. So it can't be hacked out. So use frameworks that let you authoritatively assess whether the device or application calling the API is actually what it says. So Samsung Knox is an example of a framework like this that's made some great strides, allowing you to extend a challenge and response through both the application and the device. If you're designing a web flow, another option is to call the API from a server-side application rather than from a browser-side script that anyone can download and analyze. Like I mentioned, your JavaScript is public even if it doesn't show up on the page itself. So these different patterns allow you to have a little more control over the confidentiality of your API request, if you can manage to do these without compromising the user experience, which is important, and we'll talk about more. So another method is actually provisioning an application-level secret after the app has been installed from a public app store. So you download it, and then as part of a registration step, it requires validation after that app has been installed. But then you can make the secret unique to each installation, unique to each app, each user, and that remediates the impersonation problem that we've discussed. So the difficulty here is it kind of transfers the burden, and now it's in creating and managing that registration flow in the app. But that's also something that can be handled by some application or API frameworks, including ours. And then a fourth option is simply using a private app store. So this is especially relevant in B2B use cases or business-to-employee, as B2E use cases, where your organization has an internal app store that employees download their apps from. Of course, this doesn't fully mitigate the problem. You still have to trust the people that download the app, not to reverse engineer or hack it, but it certainly limits the audience with access to the app, unlike if you put it out in a public app store like iTunes. So the next type of attack I want to talk about is a phishing attack. So these happen when the access control mechanism for the API is based on a redirection pattern. So at some point there's a redirection between different servers to complete kind of a handshake. So this is where OAuth gets blamed a lot due to its handshake model, but it actually has a bad rap here. In reality, it just means that someone didn't implement OAuth well enough to protect it from a phishing attack. So this is where a malicious application pretends to be a legitimate application. It fools you, and there's a little illustration here of a user that's redirected to an OAuth authorization server. That's where you go to actually provide your credentials and accept the handshake. As part of the handshake, that server will have to redirect you, the user, back to the application calling the API. So the way it works is you pass a redirect URI as part of the handshake, and it follows through once the authorization's been completed. In a phishing attack, a user clicks on a link or something in an app that redirects to a valid authorization server, so you're actually going to Twitter, Facebook, whatever it is, providing your credentials, but it provides a malicious redirect URL. So after you provide your credentials, you're then redirected back to a malicious site instead of the real site. So this actually happened to Facebook, as Tyson discussed. Kind of boggles the mind that they let that happen, but it did. And there were a few different vulnerabilities around that time. Our security researchers internally discovered one of them and reported it to Facebook. And there's actually already some mechanisms in place to try to avoid this. So you can actually provide a client ID to the OAuth authorization server. There's a name and a scope and some language the user is supposed to recognize and trust. So it's supposed to tell you that you're being redirected here by a specific application. But it's not necessarily always accurate, and it doesn't necessarily match up with the redirect URL. So then you put in your credentials, and when you're then redirected to a malicious server instead of a legitimate one, you provide it with a valid OAuth token meant for a legitimate application. So it can then use that OAuth token to make calls on your behalf and do something that's potentially malicious. So how do we mitigate this kind of attack? So to mitigate a phishing attack, the first thing you should always do is validate and register your redirection URI. So any API publisher should be doing that right out of the gate. So when an application is registered in your developer portal or your API management system, you should require the developers to register their OAuth callback address. So there's one or many legitimate URLs associated with the application it's expecting to redirect to. And if someone tries to insert a malicious URL to redirect to, when they do that handshake, the authorization server itself is responsible for creating an error and saying, no, sorry, this isn't a callback URL that's been registered. And so the user never gets redirected back to that unregistered and potentially malicious URL. So on top of that, you should have strict validation, not partial validation. So don't say that the outbound URL should just contain a certain string, because there are then tricky things that you can do there, like adding a suffix to a domain name or taking advantage of built-in redirection mechanisms to drive the user back to a malicious site. So they add a couple additional parameters, and suddenly you find yourself on a malicious site again. So you want to be very strict with this validation. You should also never skip the consent step. You should never skip the part where the user gets involved and allow the application to work around that user-driven acceptance. The user needs that opportunity to understand exactly what they're agreeing to, what scope they're providing, and what application they're granting permission to access a resource. So this basic phishing mitigation is something that every OAuth publisher, everyone that distributes access tokens to an application to act on behalf of a user, it should always employ something along these lines. Okay. Next is brute force. So moving on to brute force attacks. So when someone hears brute force attack, they might think of sitting there and repeatedly entering credentials into a login screen on a web app to try to guess a user's password, or even to automate that a bit and run through a dictionary of potential passwords to see if one actually is successful. But when applied to the API world, this can be even more dangerous because it's more often automated. So the example in this slide describes the Snapchat find friend exploit that Tyson mentioned at the beginning of the session. So this was caused by a feature that was really actually a great idea for encouraging their app to go viral, but it ended up becoming a vulnerability because it was not protected well enough. So Snapchat, as Tyson mentioned, is a social media app that allows you to send pictures and text to your friends that disappear after a few seconds. So it was considered a more secure way of communicating private information. And you might have been able to hear my air quotes when I said secure just now, because it's not really. There's lots of ways around that. So anyway, after downloading the app, you want to be able to quickly connect to your friends that are already using the app or recommend it to those who weren't. So the app asks for permission from the user to get a list of the local contacts on your phone in your address book. So it can see all their phone numbers. And when you register your app, you provide your own phone number. So Snapchat created an API that exposed kind of the mapping between phone numbers and existing usernames. So the app uses that to quickly build your social graph and get your friends connected to you on this new platform. It's a great tool, but there was absolutely zero security on this API beyond a shared secret associated with the application. So once it was reverse engineered, and that basically it fell victim to vulnerability number one, they reverse engineered the app, they got the shared secret, and then they were able to make calls to the API as a legitimate client. And so the list of possible phone numbers is a really well-defined space. Basically 000, 000, 000, 0000 through 999, 999, 9999. And you can narrow that down even more with some basic research about area codes and phone number construction. But even if you check all 9.999999 billion possibilities, you should still be done making those API calls in about 20 minutes and have a list of every Snapchat username tied to their phone number. So it's immediately personal information that you can actually create a database of, and that's what that Snapchat DB team that Tyson mentioned did. So what do you do about this kind of brute force attack? One of the things to keep in mind is that we're potentially talking about headless clients, meaning that the application calling the API does it machine to machine, device to device. So there's no user participating in the transaction. You don't choose to make the API call to look at the telephone number. It's the app itself doing the transaction. So you can't have just a CAPTCHA or some other user-dependent validation step in the process. You need to protect against bots that are doing that. So one way of doing that is by having rate limiting, quotas, or SLAs being enforced on the API. So you want to rate limit calls on the entry point to the API to protect your backend. Ideally, you'd want access control associated with these calls, but if you can't do that, if you can't tie it to a user, then you want to throttle, blacklist, and block any request that looks like it could be an attacker. So you want to correlate any identity you can glean about the requester, the location of the user, the concurrency of calls from any particular user or device, and if it goes beyond one, you should only be making one call for that particular API, or more, depending on what the expected behavior of that API method is. Then you suspect a brute force attack and reject the call. The other reason you want to protect against brute force and other denial of service attacks through rate limiting is to protect your backend, so they can't bring down your primary application by flooding it with requests. So this should be part of your API management infrastructure, and you should have global rate limits to guard against denial of service. So user-specific, application-specific, app-specific, as well as global rate limits. So as for the last bullet on here, when we say apply rate limiting with application-level awareness, this means you should have some understanding of various factors. So it's not just rate limiting based on an IP address or a specific user, but a combination of multiple factors, including content within the message itself, transaction metadata, and a really strong understanding of, as I mentioned before, that relationship between users, devices, and applications. I take a pause to catch my breath. Okay, so injection is something you might have heard about before in the context of SQL injection. It's one of the more common exploits of all forms of applications, including web apps. And there's even some great jokes and geeky comics about it. So in an API context, it means you have an API with some input parameters, and you'd use as a value for one or more of those parameters, a value that then gets interpreted by an application or a database on the back end and could have a malicious result. So you can see in our example here, an API that takes a transaction ID, it converts it on the back end to a SQL select statement that retrieves information about that transaction from a database, and then responds with information back to the caller. In this case, we substitute a string for the number that would always match all transactions in the database to say ID equals, and then close quotes, or 1 equals 1. So that's always going to match. And you can end up returning information about every transaction in the database. So that's an example of what we call data exfiltration. You're extracting data that doesn't belong to you. Another example might be appending a drop table statement to the end of the SQL that gets executed. So that results in your database table being wiped out. So obviously this can be a painful exploit if you don't protect against it. And not just SQL, but these can take many forms. So in dealing with XML, you can maliciously insert XPath or XQuery to do some of the same stuff. You should even inject code, JavaScript perhaps, that could later be used to capture data from somebody else that uses the same application, where it gets pulled up into their browser and executed, and then can capture some of their information. These threats can even be encoded, so it tries to obscure the true nature of the threat, as you can see in the lower right hand, where that 1 equals 1 clause has been escaped appropriately for a URL, so as not to cause an error, and you might even, just looking at that, not suspect it of causing a problem. So it's a very well-known pattern, but it's especially applicable to APIs. And in some cases, injection doesn't even have to be that complicated. So in one of Tyson's examples, attackers figured out that you could simply take a valid request, remove the account number, insert another account number, and retrieve information about other user accounts instead. So instead of getting information about your account, you just get information about a random other account. So that can be brute forced as well by going through a bunch of numbers, possible numbers, and gathering that data on responses. So it's an example of client impersonation, injection, and a failed mapping of access tokens to other contextual data, so which we'll talk about in a minute. So really this is a trifecta of API threats. Okay, so how do you protect against injection? First of all, you take the same steps that you would take to protect against any injection attack on any application, and that's input sanitization. So you parse the input parameters, so the HTTP headers, the URL parameters, the post parameters, etc., and you should know what to expect in each of those contexts when you're designing your API. You should know what should be coming in each of those places, and you should apply patterns to make sure that nothing other than what's expected can get through. So that's called defining a positive security model by allowing only certain things through that are expected. So you can use things like JSON path, XPath, XSD, that's XML schemas, JSON schema, and regular expressions to do the actual retrieval, parsing, and validation of fields before they're passed to the back-end infrastructure, before you actually allow the back-end to become vulnerable. And these all work better if you own and tighten your metadata. So what does that mean? That means don't necessarily rely on simple machine-generated schemas that might be very loose. They might say, oh, okay, this just has to be a string. These standards that we're using actually allow for very strong typing, validation of length, and structure for each field. So don't just allow a generic string. How long can the string be? If you're expecting a decimal, look for a decimal. If you're expecting a credit card, use the standards for both schemas and the industry standards for credit card number construction and validate to confirm what's there. That makes it very, very difficult to inject anything like a SQL attack. But here, security needs to happen at every level, not just filters added on at the end. So you need to do code level sanitization. You need to check your prepared statements in the database to make sure they're not vulnerable. And signature-based threat protection is useful, but not alone. So you need to do kind of a combination of both the input sanitization, kind of the positive security model, and signature-based filtering of common threats, a negative security-based model, in order to have the strongest possible protection across the board. So while on this note, I'll reiterate that security has to happen at every level. So even if there's a breach in protocol security, as in the shell-shock vulnerability that caused problems for Yahoo in Tyson's introduction, having the appropriate API and backend security can protect you against any real exposure. So you want to be doing these things at multiple levels. The last vulnerability we're going to talk about is unauthorized access. So there's lots of permutations of this. An API that should be secured isn't. An authenticated client has access to a resource that should be restricted, so you're getting somebody else's information. Or a session-based secret has been compromised by one of the mechanisms we've already discussed or some other method. So an example is the Moonpig API breach that Tyson mentioned. It was poorly authenticated. It was reverse engineered to discover that it contained a built-in secret that could be used to spoof a valid client. And other customers' ID numbers could be injected into the request to provide details about other people's accounts. So it's another threat trifecta. So the most secure API is the one that never gets used, of course. But you can't forget the user experience when you're designing the application. These APIs are meant to be used. So if you implement too much security and sacrifice the user experience, they'll actually lower adoption and guarantee failure of your mobile initiative. So there's a real trade-off between convenience and risk, and it's very important. You need to secure your APIs, but you also need to enable a positive user experience. So there are lots of ways to do this, to apply this access control and authentication and still maintain a positive user experience. So you want to apply authentication as part of that access control for your API. It should include both local auth, like a PIN or a fingerprint reader, and back-end authentication. Your infrastructure should allow you to enable an API publisher to authenticate calls using an existing identity management investment. So you already have an IAM system, you should be able to use that IAM system, or social login integration through OAuth, for instance, or federation from some other authentication provider, especially in a B2B scenario where you're working with partners. So that might be a SAML federation standard. So you really want to be able to use whatever mechanism is relevant to your use case on an app-by-app basis. You want to make it easy for people to come in with their own identity and provide the infrastructure to provision standards-based tokens based on their own identity. So to manage the lifecycle of those tokens, to allow refresh and revocation of those tokens. Those standards like OAuth and OpenID Connect support those concepts already. They have the tokens, they have the lifecycle concepts, so your infrastructure should support those standards. You should also be able to assert different levels of identity. So who's the user of this application, who wrote this application, what device is this application running on. If you have that information in the infrastructure, it allows you to develop more relevant access control rules. You might also want to define a different scope based on the user or their role. So one user would have access to a certain level of data, perhaps read-only, while another might have administrator access to manipulate data or have access to additional app functionality. So you'll need a resource server that understands those identities, understands the tokens that are coming in, and can map them to ownership of certain resources so that a user can get their data and only their data with an identity token and not necessarily with their full username and password-based credentials every time after going through authentication. So you also need to be able to map these tokens to existing tokens. If you have existing infrastructure, you want to be able to bridge something like OAuth on the front side to a different infrastructure type on the back end. For instance, a Kerberos token in a Microsoft environment or an SM session token in a CA single sign-on environment. So you need to be able to separate the internal token formats from external token formats, but maintain the relationship and access rules between them. And lastly, ideally, you should be able to add on additional access control methods on top of those I've already mentioned. So behavioral risk analysis based on the way a user is interacting with an API, or step-up multi-factor auth for an additional layer of either challenge response checks or out-of-band token provisioning, so you get texted or emailed a token, or additional validation. And so these can help you reconcile a good user experience with security by only adding additional effort on the user's part in certain circumstances. Okay, so we've talked about lots of threats today and ways to mitigate those threats, but there's obviously a lot to implement. And if you went out and bought a point solution for each of those, you'd drown just trying to install them all. So, but a comprehensive platform for API management can address all of those threats at once and hopefully do it in a way that balances security with user experience for both the application developers who need it to be developer-friendly and the app users themselves. And this is where CA API management comes into the picture. So I'll walk you through how this process works in the real world. So you'll see in the upper right the CA API developer portal. This is the design time front end for two different constituencies. First, the API publisher, who gets to create and publish APIs, define API plans and pricing, define rate limits, SLAs, threat protection, who gets access to those APIs, as well as monitoring and analytics for keeping track of how those APIs are being used in the real world. This portal is also the design time resource for developers. They come to the portal to discover what APIs are available to them, to register themselves, their organization, their applications, and get documentation and code samples on how to consume the APIs. They can test against live backends. They can coordinate with other developers to build really enterprise-class apps. And in the lower left, those apps are deployed with the embedded app security, enabling various types of standards-based authentication and threat protection. And the apps are then downloaded by the end user and communicate with the enterprise through API calls. At runtime, those API calls are processed by the CA API gateway in the lower right, which provides adaptation and mediation to the backend systems. It enables throttling and caching of incoming requests and enforces all of the access control and threat protection policies that were selected by the API publisher in the portal. So this is where all of the various mitigation techniques that we talked about today can be very quickly and easily implemented just by dragging and dropping these things to protect your APIs from threats, protect your organization from a breach, all without writing any code. So it should be code-free. You shouldn't have to be coding security. These products have the most flexible deployment model of any vendor in the space, so you can do everything on-premise, either internally or in the DMZ, with full control over your infrastructure. You can run it in a public or private cloud, or any combination, kind of hybrid combination of on-premise and cloud for easy scalability or differentiation of concerns or apps. Or you can consume our fully managed SaaS model, where you get full access to the portal and gateway interfaces without having to deal with hosting or managing the infrastructure yourself. Now, I know we're running short on time, but I wanted to just take a minute to talk about the enterprise mobility ideal. So we've already talked about trade-offs between security and user experience. Well, let's take this a step further and actually enable seamless integration between apps and between devices using the same infrastructure. So this is kind of an ideal goal for the business, the employee, and the consumer. So here's an example that describes our single sign-on across mobile applications. When you build your apps using our mobile SDK on the client and our mobile API gateway on the back end, you have the option to enable single sign-on across multiple apps. So you can actually also maintain a session context that's shared across applications. So if you open app A and authenticate yourself, you can then open app B without having to re-authenticate because the gateway recognizes the provision token and grants that access. And then apps B, C, and D can also access the session context created by app A if you so desire, and share information between apps. You don't have to redo things across apps. Not only that, but you can extend that experience across not just applications, but also across devices. For instance, you have apps on a smartphone and a tablet, and you want to transfer your session from one to the other. So we enable you to use one of several proximity technologies like Bluetooth Low Energy, NFC, even a simple QR code to demonstrate that proximity, that I am near both of these devices, and migrate the session from, say, your Android phone to your iPad without having to re-enter credentials or restart what you were doing. This kind of cross-platform session sharing is unique on the market today, and it takes advantage of our rich understanding of that interaction between users, apps, and devices. So that's a slight deviation from the specific topic at hand, but another example of how that security doesn't have to detract from the user experience. So feel free to start sending in your questions on the Q&A, and I'm just wrapping up here. So as we start to wind down, here's an overview of a report from Forrester on the API management space. As you can see, CA is recognized as a leader in this area, and we were specifically called out for having the best security, message transformation, and integration features in the entire evaluation. It also recognizes us as having the best support for mobility, based in large part on the features provided by the mobile API gateway that I just briefly discussed. And then a quick summary. So, long bit of talking, quick summary. Protect your APIs, but don't make it too difficult for your developers, and don't sacrifice the end-user experience for the sake of security. So if you leverage the appropriate API infrastructure, and I'd obviously recommend ours, you can implement those API security best practices without sacrificing your good experience for either developers or users. In fact, you can enable rapid app development with state-of-the-art protection, so you don't have to read about your organization in the news in yet another API breach. So we'll be talking about these topics and many more at RSA and the Cloud Security Alliance Summit in April. We'll have a booth at RSA with solution demos. Our VP of Security Solutions will be giving a presentation on the new security reality in the application economy. And our Executive Vice President, Amit Chatterjee, will be giving a keynote at RSA entitled Security Rewritten by the Application Economy. So join us there, check this out. And with that, thank you very much for attending and sticking around until the very end. So let's wrap up and get to any questions.
Great, thanks, Jamie. Very informative. So there's a couple questions that came through. One was hitting on kind of that, that conversation around, enabling and protecting the business. So obviously, common security obstacle is, the fact that potentially security could inhibit the business. So for those mitigation steps that you provided, could each of those be applied potentially in the context of the breaches that we discussed in a way that wouldn't have detracted from the business objectives that they were trying to achieve, or potentially the user experience. So I guess another way of saying it is, could they have applied security that in a way that one, could have provided effective or adequate security, but not take away from the user experience or the app experience.
Yeah, absolutely. Because all of those threats were taking place at the API layer, most of the protections against them wouldn't have been noticed by any end user. So, and even the developer wouldn't necessarily have to code that into their app, because it can be done at the infrastructure layer. So you can put things in place like SQL injection protection, code injection protection, a well-designed OAuth handshake with appropriate redirect checking and validation. All of those things are completely transparent to the end user. Moreover, if you want additional security like two-factor auth, even that doesn't have to present a burden to every user. You can use things like risk analysis, behavior analysis, to determine whether the user is behaving in a way that is different. So if they're using a different browser all of a sudden, or they're coming in from two different locations, or a location that you don't recognize, or a device that you don't recognize, you can actually step up that authentication only in those cases. So if somebody is just continuing to use the app as they always have, they wouldn't even require a second level of auth.
Okay, great. Looks like we have some questions that are starting to roll in here. The most recent was around threat protection itself. So it seems like threat protection varies a lot based on APIs. Do you see a must-have, nice to have, or even an optional list that should be applied in general to all APIs?
Sure, absolutely. So it does vary a lot on APIs. You have to be very aware of kind of how your application works, what potential back-end vulnerabilities are there that you might need to protect against for a given API. But yes, there are absolutely must-haves. All of the ones we talked about today are must-haves. You absolutely have to protect against things like code injection. There are lists of top 10 vulnerabilities produced by organizations like OWASP out there. You have to be aware of those. You have to authenticate and go through validation of your inputs and redirection URIs and other things that relate to the handshake. The trick is to only have to put together that must list once. And even the kind of nice to have list, you can put that together once as well, and then reuse it across all of your different APIs. So our solution offers you the ability to put together those threat mitigation steps and then save that as a reusable piece of policy. So any REST API might have the same set of 5 or 6 protections up front. Any XML-based API might have a similar but slightly different step that uses XML schema rather than JSON schema, for instance. So yes, there are absolutely kind of must-haves, nice-to-haves, and optional lists. And if you put those together into nice consumable packages, then really the infrastructure team can throw those in on any API.
Okay, great. Got a couple more minutes here, and I think some more questions. This one was more around authentication as it relates to mobile. Dual authentication, specifically, does dual authentication fit into this model? Do you have some thoughts that you can share there?
Yeah, so really as many types of authentication as you'd like can be applied to any of these implementations. So you can have two-factor auth for everybody. You can have two-factor auth based on some other criteria. You can require an API key and an OAuth handshake and a shared secret, or a hash, so it's entirely up to you. You can mix and match, and really you want to make it applicable to the API that you're exposing. For some APIs, you might only require a social login. You might they might not be need much level of security, just kind of an identifier, and so you can allow a Facebook token or a Google Plus token or a Gmail username. In other cases, you might want much more. You might want to validate against an internal LDAP directory or a list of users, or so it varies depending on your API, but certainly you can implement as many or as few of these as you'd like.
Very good. And so we have 1 minute left. You see that question there around OAuth. Any thoughts there?
Yeah, it's related to OAuth, where user authentication is delegated to the service provider, but the URL is provided by the authorization server. So OAuth is really all about trust. So if you trust that authorization provider is going to provide the appropriate redirect URL, then great. If not, then you should be validating it as well. I mean, you always want to know kind of deterministically ahead of time where the user is going to go, especially when it comes to redirect. If they get redirected to a service provider for authorization, then you want to make sure when they come back, they're going to be going to the right place, because that token that you get back is pretty powerful, and if you end up on a malicious site, it could really be abused.
Great. Thanks, Jamie. A lot of good information there. Thanks for the presentation. Thanks for the detailed explanations as well. We're up against the hour here. And thank you, everybody, for joining today's webcast. Please be on the lookout for some additional information tomorrow. We'll be sending over this presentation as well as some relevant collateral that should help you in your API and management and security projects. So thanks, everybody. Have a great day.
Thanks so much.